Okay, so, this chapter has been about, computing a probability, basically how to analyze an experiment, okay, whose outcome is random. Okay. And so what we do is we first analyze the possible outcomes, and then we attach probabilities to those outcomes, and then compute, ask a question which defines a subset of the outcomes, and then compute the probability of that subset. Okay. And so read chapter 15 carefully, okay, and do all the exercises and become good at computing probabilities. Now I want to show you something, a little bit more complicated, and that's how we'll end this lecture. Okay. Which is we'll answer the second question that was posed at the beginning, which is you toss or you flip a coin, okay, randomly until heads. Okay, how many flips do you make? How many flips do you make? Okay, so let's analyze this. Okay, so let's see how this experiment goes. In the first flip, one of two things happens. You get a head or you get a tail. Okay, just like the regular situation of flipping coins. Okay, now if you get a heads, the experiment's over because you flip the coin until you got a head. Okay, so the experiment's over. But if you get a tail, the experiment is not over yet. Okay, so you have to keep flipping until you get a head. So you'll flip again. You could either get a heads, or the problem is you could get a tail. Okay. In this case, okay, here the outcome is H. Here the outcome is TH. Here the outcome is not yet determined. The experiment is not yet over. So you keep flipping. You can get a heads or you can get a tails. Okay, so here the outcome is TTH. You stop. And problem is it's not yet over. So you flip again. H or tails. And here the outcome is TTTH. Okay. When will this experiment end? This is a bizarre experiment. Okay, this is a bizarre experiment. It can go on forever. This experiment can go on forever. Okay, but that's not a problem. Okay, there's nothing that says an experiment has to terminate. Well, eventually, when it stops, it'll terminate with a finite number of flips. But when we're considering what are the possible outcomes, they can go on forever. In principle, you could toss any number of tails before getting the first head. Okay. Now, so the outcomes are H, TH, TTH, TTTH. Then the next one here would be T, 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 TH. So we can write this as T cubed H just to be simpler. Okay, and then the next one would be T to the fourth H, and then T to the fifth H, and so on. Okay, so if I'm writing my outcome space, okay, to look at my probability space, my outcome space consists of H, TH, T squared H, T cubed H, T to the fourth H, T to the fifth H, and so on. So my sample space, my set of all possible outcomes is infinite. Okay, that's why I said this is a slightly more complicated, example. And now what are the probabilities? Probabilities. Okay, so associated with this sample space, to get a probability space, I need to assign probabilities. Okay, and so let's see. So let's just do it the usual way. So you have a half here, a half here, a half here, a half here. That's because each toss is a fair coin. Okay, so a half here, and so on. So the probability of this guy is a half. This guy, half times half. So 1/2 squared. This guy, half times half times half. 1/2 cubed, and so on. So this is a half squared, a half cubed, a half to the fourth, a half to the fifth, and so on. Okay, it's not a uniform probability space. Okay, but is it a probability space? So are all the probabilities non-negative? Yes. Do they sum to 1? Let's see. So 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth plus that is equal to 1/2 over 1 minus 1/2. So this is the famous infinite geometric sum, and if you don't know about it, read up about it in the summation chapter where we gave you the common sum for a geometric progression. So, or take this from me. Hopefully you've seen it before, the infinite geometric sum, and this is equal to 1 as expected. Okay, now interesting question. So let's analyze now an interesting game. Okay, so you and a friend decide to toss coins. Okay, you flip a coin. Okay, and the first person to get a head wins. So take turns, first head wins. Do you want to go first or second? Okay. So let's see. Let's imagine that you go first. So this is an example of, you're taking turns to succeed, and do you want to be the first to get a chance to succeed or the second to get a chance to succeed? So let's say you're the first to get a chance to succeed. When do you succeed? You succeed here. Okay, you succeed. So you win. You win, you lose, because you tossed a tail and then your friend tossed a head. Here you win because you tossed a tail, friend tossed a tail, you tossed a head, so you win. Here you lose, okay, because you tail, friend heads, so friend wins. Okay, here you win, and so on. You see that the outcomes that correspond to you winning are exactly the odd powers of 2. So the first head wins. So the event that corresponds to you winning is the event, h t squared h t to the 4th h, and so on. Okay. And the probabilities of these are 1/2 cubed, 1/2 to the 5th, and so on. So the probability of this event is equal to 1/2 plus 1/2 cubed plus 1/2 to the 5th plus and so on, which is equal to 1/2 over 1 minus 1/4, which is equal to, so the common ratio between these terms is 1/4. So the sum of the infinite geometric progression is the first term divided by 1 minus the common ratio, okay, which is 1/2 times 4 over 3, which is 2/3. Ah, interesting. So we've come up with an interesting sort of tidbit. Okay. If you're engaged in this game of you try something, okay, and if you win, game over. If you fail, I try, and if I win, game over. You try, I try, you try, like that. If you're interested in this kind of, if you're engaged in this kind of a battle, okay, then going first gives you a 2/3 chance of winning. Question: what about going second? So your friend, what are your friend's chances of winning? So probability that first wins equals 2 over 3. What about the probability that the second wins? Okay, now we could compute this complicated summation again, or we could realize that either you win or the second wins, either first wins or second wins. So so the probabilities of those have to add up to 100% or 1. So this must be 1/3. So your chances of winning in such a battle are twice as likely if you go first. So be the aggressor, go first. Okay. And this kind of analysis applies to all kinds of situations. For example, a startup. If you're the first to market, you are much more likely to be the winner than if you're second to market. Because if you're first to market, you are the one who get the first customers. Okay, with high probability, with let's say probability 1/2. You might not get the customers, okay, and then the second to market might get the customers. But then if they don't get the customers, now it's your chance again to get the customer, and so on and so forth. Okay, so this kind of a tit for tat battle that keeps going on occurs often in practice. Okay, and here's an analysis that shows if you're first in this attempt to win, you are twice as likely to win. Okay, so that's probability. Some of the uses of probability. Okay, read chapter 15 carefully. Get good at computing probabilities. Checking out.